Hey everybody. Last week we looked at two different ways that we can test for a relationship between two variables when both of those variables are continuous, meaning they're both numbers. First, we looked at Pearson's R statistic, which a lot of you were familiar with already. Remember that R can be anything between -1 and +1. The number tells us how strong the correlation is. So if there's a correlation of 0, it means there's no relationship whatsoever. And as the number gets further away from 0 in either direction, it means the relationship is getting stronger. The sign of R, whether it's positive or negative, tells us the direction of the relationship. So if R is positive, it means that both variables move in the same direction. As one of them goes up, the other one also goes up, or if one goes down, the other one goes down. A negative correlation means they move in opposite directions. So as one goes up, the other one goes down. You might also hear that referred to as an inverse correlation. We talked a little bit about scatter plots, a graph that we can use to visualize a correlation where each person is one dot on the graph, and the position of their dot tells us their score on both of the variables. And we talked about how you can look at the overall pattern of the dots to get a sense of both the strength and the direction of the relationship. We also talked about how you can envision drawing a line through the dots that sort of moves in the general direction that the relationship is headed, either upward or downward, depending on whether the relationship is positive or negative, or if there's no relationship, that line will just be pretty flat. But a more formal way to do that, rather than just picturing it in our heads, is to calculate a regression, which is going to tell us what the best possible line is that we can use to summarize this relationship. The first thing we did, since we're going to be spending the next couple weeks talking about regression, we talked about some of the lingo that we're going to see coming up when we talk about regression. So first thing, regressions can be either linear or logistic. A linear regression means that the thing we're trying to predict is a continuous variable. The thing we're trying to predict is a number for linear regression. Next week, we're going to talk about logistic regression, which is very similar, but the difference is the thing that we're trying to predict is what category a person belongs to. We've only looked so far at simple regression. Simple just means there's only one predictor variable. But in a couple weeks, we will look at multiple regression, where we have multiple variables that we're using to predict some outcome. One thing we talked about last week is, at least in theory, the more variables we have, meaning the more information we have, the better we should be able to predict whatever the thing is that we're trying to predict. But that only happens, of course, if those variables are actually giving us useful information. So as we saw last week, what a regression does is it mathematically calculates the best possible line to summarize the correlation between these two variables. And we talked about how we can use a familiar old formula. In this case, it's y hat equals alpha plus bx to represent the exact position and slope of that line. It's literally the same thing you learned back in high school, right? So the intercept now is called alpha. Alpha is the predicted value of y for a person with an x score of 0. And obviously on our graph, it's where the line crosses the y-axis. B is the slope. So every time x increases by 1, how much do we expect y to change? How much will our prediction of y either go up or go down? That's what B, the slope, is going to tell us in a regression line. Now, another thing we talked about last week, and this is going to come back up again today, is that our predictions aren't going to be perfect, right? We hope that knowing this predictor variable x will allow us to make better predictions of the outcome variable y, but there's still going to be some variability, right? Some of our predictions are probably going to be quite good, meaning the dot is very close to the regression line, but for other people, our prediction might be quite bad, meaning the dot is kind of far from the regression line where we predicted that person was going to end up. So what we could do, and in fact what we're going to do later today, is for each person we can calculate what's called a residual, which is just a measurement of how far off our prediction is. So if our prediction's pretty far off, like it is for this person right here, their residual is going to be fairly large. But if their dot is pretty close to the line, telling us that our prediction was pretty close to their actual score, their residual is going to be pretty small. What we hope is that most people have residuals that are pretty small, meaning we're hoping that most of the dots are fairly close to our regression line, and there aren't as many dots that are farther away from that regression line. Because what regression actually does is it calculates the quote unquote best possible line by figuring out how to make the line as close as possible to as many of the dots as possible. To practice this, I left you with a practice problem where the researchers collected data from a animal shelter, and they wanted to know if dogs who have more human sounding names tend to get adopted more quickly. So we're talking about, is this a name that could be given to a human as well as a dog, or is this a name like brisket that's probably not going to be given to a person, but could be given to a dog? So here's the data file that you would have used if you did this practice problem. For each dog, we know two things. First, we know what percentage of participants in sort of a focus group type pilot study, how many of those people judged the dog's name as non-human. So that's the one thing about this example that was kind of tricky. I'm not sure why the researchers did it this way, to be honest, but for this non-human variable, a higher number actually means that the dog's name is less human sounding. So, brisket, for example, might have a 90.72, but then that 0.33 might belong to Carly, which is a very sort of ambiguous dog human name. And then, of course, for each dog, we know how many days it took for them to get adopted from the shelter. So we would run a linear regression here by following the steps that we did last week. Our predictor or X variable is going to be what percentage of people judge the dog's name as not human. And our outcome or Y variable is going to be how many days it took for someone to adopt the dog. I asked you to practice writing this up in APA format, try to make a scatter plot if you felt so inclined, and tell me what the numbers alpha and B are and what they mean in the context of this problem. So if you ran the test, the output would look like this. Remember, the first place we have to look is at our p-value. The first thing we have to do is figure out, is this a significant relationship or not? In this case, it was. Very, very small p-value, less than 0.001, telling us that this is, in fact, a statistically significant relationship. The next thing we would want to know is whether this relationship is positive or negative. To figure that out, we could look at the t-statistic, which in this case is positive 5.15. Since the t-statistic is positive, it tells us that the relationship is positive. So the more non-human a dog's name sounded, the more days it took for them to get adopted. Alternatively, we could say that the less non-human, which is another way of saying the more human a relationship or a dog's name sounds, the faster or the fewer days they would get adopted in. Here is a scatter plot, as you probably already figured out, of every dog in this study. Pretty weak relationship here, right? As you can tell from the how spread out all of these dots are. There was a lot of variability in terms of how long it took these dogs to get adopted. But there was nonetheless an overall, even though it was weak, an overall significant positive relationship between these two things. Next, we're going to look at the value of alpha, which in this case was 9.07. Remember that alpha is the predicted value of y, in this case for a dog, with an x score of 0. So if everyone judged this dog's name as human, or in other words, no one judged this dog's name as non-human, we would expect a dog like that to be adopted after 9.07 days. Below that, we have the value of b, our slope, which will round to 0.05. What that tells us, remember, is every time x increases by 1, how much does our prediction of y go up or down? In this case, every time x goes up by 1, our prediction of y goes up by 0.05. So in this context, it means that for each additional 1 percentage point of people who judge the dog's name as non-human, so for every 1 point increase in the, quote unquote, non-humanness of the dog's name, we would expect the amount of time that they take to get adopted to increase by 0.05 days. So again, that's consistent with a pretty weak relationship here, right? 0.05 days is not a huge change for every 1 point increase in the non-humanness of a dog's name. But the point here is there was indeed a weak relationship between how non-human a dog's name sounded and how long it took for them to get adopted from an animal shelter. As I always recommend, if you did this practice problem to check your own understanding of this stuff, take a moment. You can even pause the video if you need to for a moment. Compare the answer you got against the answer I got. And if you have any questions or see anything confusing, I would say either email me or better yet, bring it up in class next week, just in case someone else might have the same question as you. So now moving on to new stuff. It's new in the sense that we haven't talked about it before, but we're actually doing the same test that we did last week. We're just going a little deeper into it than we did last week. So everything we're doing today is again going to be a simple linear regression, meaning we have one predictor and we're using that one predictor to try to predict a thing that is continuous, a thing that is a number. What's going to be different is we're going to look at some additional things that we can do with this analysis that we didn't look at last week, including some of the output that we originally just skipped over. We're going to take a little closer look at that now and see if it tells us anything useful. Our first example looks at this sort of personality trait called maximizing versus satisficing. So these two concepts kind of fall on a spectrum, right? Most people are either more of a maximizer or more of a satisficer, and then other people might fall somewhere in between. A person who is a maximizer, when they're making a decision, is the sort of person who looks at every available option to make sure that they're making the best choice. So they're only happy with the best possible option. On the other end of the spectrum, a person who's a strong satisficer doesn't do that. They only look at as many options as they feel like they need to look at until they meet one that's good enough, and then they go with that and they're happy with it. So you can think about a lot of ways that this might manifest in people's behavior, right? One thing I always think about is if you're at the grocery store and you're buying like an apple or an onion, how many do you look at before you pick one? Right? If you're a maximizer, you probably stand there and look at 20 different apples and try to find the one that's the best, whatever that means to you, before you throw it in your basket. But if you're a satisficer, you probably look at one or two and you're like, yeah, this looks fine, and you throw it in your bag and you go on with your day. Obviously, it's not that one of these things is better or worse than the other. It's just different ways of sort of making decisions. Um, Same goes with if you're dining out at a restaurant, right? Are you the sort of person who reads the entire menu to make sure that you're choosing the best possible dish? Or do you just read the first couple and as soon as you see one that sounds good, you say, yep, that sounds great. That's what I'm going to do. Are you the sort of person who checks to see what's on every single TV channel before you pick something to watch? Or do you stop as soon as you see something that looks good, right? That's what we mean by maximizer versus satisficer. Um, there's been a lot of research on this concept in the field of behavioral economics because, as you might imagine, being a maximizer versus a satisficer really influences consumer behavior, right? Imagine you're buying a house or a car or a new phone, right? If you're a maximizer, you're going to do a lot more research, read a lot more reviews, that kind of stuff, and make a more careful decision. Whereas if you're a satisficer, you're more likely to just pick, oh, yeah, this one looks good. I'm satisfied with it. So here's an excerpt from a study where they found that people who were more stronger maximizers toward that end of the spectrum, they did more product comparison, meaning they did more research, read more reviews, that kind of stuff before they made a purchase. They engaged in more counterfactual thinking. So after they made a purchase, they were more likely to think, well, what if I had bought that car instead of this car? Or what if I had gotten that meal instead of this meal? And to go along with that, they experience more regret over their purchase if they ultimately feel like they didn't pick the best one. If you're curious, you can pause now. This is actually a scale that was developed to measure the extent to which a person is a maximizer versus a satisficer. Let's pick one of these items at random. Number 5, I often find it difficult to shop for a gift for a friend. A person who's a maximizer would probably say, yeah, I find that really hard because I want to make sure that I'm getting them the best possible gift. But if they're more of a satisficer, they probably shop a little bit and they say, oh, I think my friend will like this, and they get it, and they probably have a much easier time picking something out. So the first example that we're going to look at today was a study of how the tendency to fall on either the maximizer versus the satisficer end of that spectrum is related to people's job behavior, specifically applying for jobs and being satisfied with their jobs. So in this study, they gave each participant a personality test that measured the extent to which they were more of a maximizer, more of a satisficer. So everybody got a score that indicated where they fall on that spectrum. And then they tracked some behaviors of these people when they were on the job market. How many jobs did they apply for? How often did they seek out advice from other people? How often did they fantasize or regret about jobs that they had applied for or accepted? And then some more tangible measures. What was the starting salary at their job when they actually decided on one? And how satisfied were they with their job when they actually decided on one? So for this first example, we're going to look to see if there was a relationship between a person's maximization score, that's going to be our X or predictor variable, and their starting salary when they actually picked a job. That's going to be our outcome variable. And again, since that's a number, right, salary is a continuous variable, we're going to use simple linear regression here to see if, in fact, these two variables are related to each other, and if so, how. As a reminder from last week, what you're seeing on the screen is how to run this test in SPSS. We're going to go to Analyze Regression Linear. Our X variable, which in this case is maximization score, is going to go in our independent variable box. I should have mentioned this earlier, but for this variable, higher scores mean you're more of a maximizer, whereas lower scores mean you're more of a satisficer. Our outcome variable is the starting salary at their job, just measured in dollars. So we're going to put that in the dependent variable box. Now, when we ran this test last week, I told you there's 4 boxes that pop up in the output window, but you can skip right to the last one, right? Because that's where the most important information is. And that's still true. But let's take a closer look at some of the information that we skipped over last week and talk about what SPSS is actually telling us, particularly because some of this stuff is going to come up again in future weeks. So I want to make sure to put it on your radar so that you know where to find it when we eventually need to use it later. This first table basically just reminds us what our variables were. So it reminds us that our X variable, which is in under variables entered, was maximization score, which can range anywhere from 1 to 9. Again, with higher scores meaning you're more of a maximizer and vice versa. And then below the table in a little footnote, SPSS reminds us that our outcome variable, the thing we're trying to predict, is a person's starting salary at their job once they finally accepted a job. So not a whole lot of information in this table, but it is a nice reminder. We can always, check to make sure we put the right variables in the right place and that kind of stuff. Below that, we have a box called Model Summary. Now, in this case, since we only have one predictor and one outcome, that first number that I have highlighted in blue, that's actually our Pearson R correlation. So we don't need to run a separate correlation here. It's actually hidden in the same output in the regression. So in this case, the correlation between maximizing score and starting salary was positive 0.34, which would be a moderately strong positive correlation, suggesting that generally speaking, people who scored higher in maximization tended to have higher starting salaries as well, whereas people who were lower, meaning they're more satisficers, they tended to have lower starting salaries. That kind of makes sense, right? If you're a maximizer and you're really holding out for the best possible option, for a lot of people, that might mean the highest possible salary. So if you're more of a maximizer, you might end up with a higher starting salary at that job. Next to Pearson's R, we have a statistic called R squared. Now, this statistic isn't really going to become important for us for a couple weeks, but I want to at least put it on your radar as something to start thinking about. Think about R squared this way. Mathematically, it's literally just taking Pearson's R statistic and squaring it. So if we were to take 0.338 and multiply it by 0.338, we would get 0.114. That's how it's calculated. That isn't so important. What I care more about is conceptually what it means. Here's how I usually think about R squared, okay? R squared is kind of like putting a puzzle together. We have this thing that we're trying to predict. In this case, it's a person's starting salary. And our goal is to make our predictions as good as they possibly can be. If we know nothing about a person, like we talked about last week, we would just guess that everyone is average because we have no information. And in a situation like that, R squared would be equal to 0. We don't know anything about this person to tell us their starting salary. In theory, the more information we learn about the person, the better and better and better and better our predictions of their salary should get. So think of it this way. It's almost like you're putting a puzzle together. And R squared is telling you what percentage of the puzzle you've completed. If you don't have any information, you don't have any puzzle pieces, you haven't put together any of the puzzle. So your R squared is going to be equal to 0. In theory, if you had a lot of information about these people, you have a lot of puzzle pieces, meaning you've built a big proportion of the puzzle. In this case, R squared equals 0.114. The way we're going to interpret that is we're going to take the decimal point, we're going to move it over 2 places, and we're going to say R squared equals 11.4%. Now, the way R squared is going to be explained in a textbook is what you're seeing on the slide right now. Maximization explained 11.4% of the variation in starting salary. Now, to the average person, myself included, that means very little, right? To me, it's easier to think about it as there's a puzzle I'm trying to put together, and by knowing a person's maximization score, it's allowed me to complete 11% of the puzzle. So if you're an optimist here, you're saying, great, I've completed 11% of the puzzle. I know a thing or two about how to predict a person's starting salary. The bad news is 11% is still nowhere near 100%, right? So our predictions might be okay, but there's still a lot of the puzzle that we haven't been able to fill in yet. Specifically, the other 88.6% of the puzzle we haven't put together. And that's basically just acknowledging that, yes, maximization is related to salary, but there's probably also a whole bunch of other variables that are related to salary as well. And since we didn't include those variables in this analysis, they're missing, right? They're missing from our puzzle. Where this is going to come up in future weeks is when we have multiple predictors, when we're doing multiple regression. What we're going to be able to do is actually look to see if those additional variables are giving us additional puzzle pieces that are increasing R squared and making our predictions even better. Okay, so again, it's not super important that you fully understand this right now, but hopefully that analogy at least makes it a little more palatable. And this will come back up again. We'll talk about it again in a couple weeks in the context of multiple regression. Here for what it's worth is how you would visualize R squared. Again, kind of going along with the puzzle analogy, if we have no puzzle pieces, then we're just going to draw a straight line and call it a day, right? We have no information about this person. We're just going to assume everyone is average. And when that happens, we're going to have some pretty big residuals, right? Some of our predictions are going to be pretty far off. But if we add a predictor, what happens if that predictor is in fact useful? Our residuals are going to get smaller, right? We adjust our regression line and our predictions get better, so the residuals get smaller. If you compare the size of the residuals on the left against the size of the residuals on the right, and you imagine sort of adding them all together, the total length of the red lines is less than the total length of the blue lines, right? So that's basically what R squared is doing, is it's kind of tweaking our regression line, making sure that our predictions are as good as they possibly can be. And again, the way we make them better is by collecting more useful information about the people who we're trying to make a prediction about. Okay, back to our output. There's one other number in that model summary table that I want to bring to your attention. SPSS calls it the standard error of the estimate. Textbooks usually call it the root mean squared error, or RMSE, which people call Ramsey for short. So we're going to call it Ramsey. Now, I don't want to get too abstract here, but what Ramsey is imagine, each person has a residual, which we just talked about. Imagine we calculated the size of each person's residual, and then we actually calculated how spread out those residuals are, right? Some are going to be really small. Hopefully, most of them are going to be really small. Others are going to be really big. We could calculate the standard deviation of those residuals to basically tell us how good the average estimate was. That's what Ramsey is. So if you only know one thing about Ramsey, it's that Ramsey is a measure of how good our predictions are. The smaller Ramsey is, the better our predictions are. The bigger Ramsey is, the worse our predictions are. So in this case, Ramsey is equal to 9,982, and it's dollars since we're talking about salary. Now, here's the thing you can do with Ramsey. You may remember from last semester or from another stats class talking about something called the empirical rule, which works like this. If you have a normal distribution, we can slice that normal distribution up into slices where each slice is one standard deviation wide. And if it is in fact a normal distribution, we can estimate the percentage of people that fall within a given range, okay? So 68% of people would be within plus or minus one standard deviation, 95% of people would be within plus or minus two standard deviations, and so on. Ramsey follows that same rule. So if we know that Ramsey equals $9,982, what that's telling us is that 68% of people have a residual that is smaller than that. Or an even easier way to think about it is 68% of the time, we can predict a person's salary within plus or minus $9,982. Now, that's not great, right? We're basically saying about 2/3 of the time, or for about 2/3 of people, we can predict their salary within plus or minus 10,000-ish dollars. But if we were to add more variables here, what we should see is that Ramsey goes down and down and down and down, right? So the more variables we have, the more information we get. If in fact that information is useful, we're going to see two things. We're going to see R squared go up, and we're going to see Ramsey go down. And both of those things are indicating that our predictions are getting better. Bigger R squared and smaller Ramsey means our predictions are gradually getting better. The third table, again, we're going to skip through pretty quick, but we will come back to it in a couple weeks, again, when we talk about multiple regression and we have more than one predictor. What this F test is telling us is whether the entire model, right? Model is just a fancy word for all of the predictors combined, whether the entire model is significant. Now, the reason we don't really care about that here is because we only have one predictor, right? So that one predictor is the whole model. It's just kind of redundant. But if we had multiple predictors, as we'll see in a couple weeks, we could either look at each predictor individually, or we could look at all of them combined. And if we wanted to look at all of them combined, this is the table where we would look to do that. Again, just putting this on your radar for now. We'll come back to this in a few weeks when this becomes more important. Finally, the part that we already know is, in fact, maximization a significant predictor of a person's starting salary? First place we're going to look is the p-value, and the p-value here is 0.001. That's obviously less than 0.05, so there is a relationship between these two things. Is that relationship positive or negative? We actually already know it's positive because we saw that R was positive a few minutes ago. But we also see here that the t statistic is positive, positive 3.46. So again, what we know from that is that people who scored higher in maximizing also tended to get higher starting salaries at their job. Like we did last week, we can also look at the values of alpha and B and explain what exactly those things mean. Both of these things are called unstandardized coefficients, right? You see that at the top of the column in that bottom table. Unstandardized just means that they're measured in the same units as the outcome variable. So in this case, our outcome variable is salary in dollars. So these numbers highlighted in pink are both measured in dollars. So as we saw last week, alpha is the predicted value of y for a person with an x score of 0. In this case, having an x score of 0 would mean you have a maximization score of 0. So if a person has a maximization score of 0, our best guess is that their starting salary is going to be about $25,600. Below that, we see the slope, which is positive, because we have a positive relationship here. Remember, the slope tells us every time x goes up by 1, how much does our prediction of y go up or down? In this case, every time x goes up by 1, meaning every time your maximization score increases by 1 point, we would expect your starting salary to increase by about 2,600 bucks. Okay, so a person with a maximization score of 3, we'd expect them to make about $2,600 more than a person with a maximization score of 2, and so on and so on and so on. Now, in contrast to these unstandardized coefficients, SPSS also gives us something called a standardized coefficient. Again, sorry to keep repeating myself, but this will become important when we get to multiple regression, and we'll see what we can do with that. But the cool thing about standardized coefficients is it gets rid of the unit of measurement. So this isn't measured in dollars anymore. This is just a number, kind of like a z-score, if you remember those from basic stats. And as we'll see in a few weeks, what the standardized coefficient is going to allow us to do is compare different predictors against each other. So it quite literally gives us a way of comparing apples and oranges if we say have two predictors and we want to know which one's better, which one's stronger. All right, so to put a bow on this thing, we will write up our results in APA format. We're going to add a few things that we didn't include last week, but that we now know how to do. So we did a simple linear regression, and the results showed us that maximization score was a significant predictor of starting salary. Now, in addition to including T and P from last week, I also included here the value of unstandardized beta, or I'm sorry, standardized beta, which was highlighted in red on the last slide. It's that very last number we talked about. Notice that for standardized beta, we use the Greek letter beta, whereas for slope, we just use the Latin letter italicized B. Um, the other thing we can add to our write-up is an explanation of how much of the puzzle we've been able to figure out. So in this case, R squared equals 11.4%, which means that maximization, which was our only predictor here, explained 11.4% of the variance in salary. If we want to be even more specific, we can interpret the value of the slope. For every 1 point increase in a person's maximization score, we would predict their starting salary to go up by $2,630. That was our slope. Okay. A couple quick things I want to point out here. First, as you probably figured out already, all of these numbers are color coded to where they came from in the output on the previous slide. So if you're ever unsure where a number came from, look back, find the matching color. That's where that number was calculated. The other thing I want to reassure you is that on an exam, I will always be very clear about what information you need to include in your write-up. Okay, so if I want you to include standardized beta or I don't want you to include standardized beta, if I want you to include R squared or I don't want you to include R squared, if I want you to explain alpha or not to explain alpha, I always try to be very, very clear about what you should include and shouldn't include. But as a general rule of thumb, the reason I put so much time into these write-ups is so that you can use them as examples and try to make your own write-ups look like this one. So on that note, if we were together today, this is the point at which I would pause and give you each an opportunity to practice this on your own in our computer lab while I went around and answered any questions you might have. So if you want, what you can do in just a second is pause this video and try doing this for yourself. Using the same data file, we also know for each person in this sample their job satisfaction score on a scale from 1 to 9. Higher scores mean they were more satisfied with their job. So what I'd like you to try doing is run another linear regression, but instead of using maximization to predict salary, I want you to use maximization to predict job satisfaction. And then, interpret the results in the way that we just did and write up your results following the APA format on the last slide. So if you want to go ahead and do that, take a few minutes. You can pause your video right now. And the next thing I will do is go over the answer to that practice problem. All right, so did maximization score predict job satisfaction? If you ran this linear regression, you would see that these two things were related to each other, but this time it was a negative relationship. So a simple linear regression revealed that maximization score was a significant predictor of job satisfaction. Our standardized beta was negative 0.25. t-statistic negative 2.44, and p-value significant 0.017. Overall, we only accomplished 6% of the puzzle here. So maximization score explains 6% of the variance in job satisfaction. The other 94% not explained yet. We haven't put that part of the puzzle together yet. That kind of makes sense, right? There's probably a lot of other variables that are related to a person's job satisfaction other than just this one personality trait. If we look at the slope, what we see is that for every 1 point increase in a person's maximization score, we would predict a 0.35 point decrease in their job satisfaction. So as maximization score goes up, job satisfaction goes down, and the slope tells us about how much it tends to go down. So the good news for maximizers is you'll make more money. The bad news is you'll be less satisfied with your job. Uh, Whenever we do an example like this that's based on a real study, I like to show you how the authors actually wrote up their results by showing you a screenshot from the published paper. So here is a screenshot from that paper. As you can see, we already found a couple of these things. So participants with higher maximizing scores applied for more jobs. They fantasized more about jobs. They wished they had applied for even more jobs. They sought out advice more when they were seeking jobs. As we just saw, they tended to make higher starting salary, but they also experienced greater negative affect related to their jobs and less satisfaction with their jobs. So again, kind of a double-edged sword here to being a maximizer. From a statistical standpoint, one thing to notice about this write-up is they report not only the standardized betas, so like up here, for example, for salary, we've got a standardized beta of positive 0.20. Below that, they also report the unstandardized beta, which is just a fancy way of saying the slope. Every 1 unit or 1 point increase in maximizing score was associated with a $2,600 increase in salary. That's the same number we got when we did it just a few minutes ago. For this next example, we're going to go under the hood, as I like to say. Rather than just driving the car, we're going to look and try to get a sense of how the car is working, or in some cases, maybe not working. As you know, a lot of the tests that we use in statistics and in science in general rely on certain assumptions needing to be met in order for that test to work properly. We also saw a little bit last week how having outliers in your sample can dramatically affect the relationship between two variables. So what we're going to do next is do regression once again, another simple linear regression, but we're going to add a few extra steps, a little quality control, I guess you could call it, to make sure that the regression is working the way that it should. So here's stuff that we've talked about before. We know how to run the test. We know how to interpret the output. We know that the t-test is what tells us whether it's significant or not. We know where to find alpha and b and how to interpret what those mean, the intercept and slope. And we also just learned two different ways to get a sense of how good our predictions are. If R squared is high, that means our predictions are good. If Ramsey is low, that means our predictions are good. Obviously, high and low is going to depend on what exactly we're measuring. So usually we're talking about like if R squared goes up, it means our predictions got better. If Ramsey went down, it means our predictions got better. Now, here's some new stuff that we haven't talked about yet. First, we saw last week how even having one outlier in your sample, right, one dot on your scatter plot that's way far from all the other dots can really throw off your Pearson R statistic and really change how the relationship looks. So it would be helpful if we had a way to figure out, other than just eyeballing it from a scatter plot, if we had a little bit more precise way to figure out whether there's any outliers in our sample or not. And if there are, we got to make a decision about how we're going to deal with them. So the first thing we're going to talk about is how to do that. Second, there are three assumptions that need to be met in order for a linear regression to work properly. Now, usually I don't really harp on assumptions too much, but as we will see, when these assumptions are violated, it might actually clue us into something interesting about the relationship that we otherwise might not have noticed. So those three assumptions are called linearity, homoskedasticity, and normality. And we'll see how to check for each of those as well. Here's the example that we're going to use. Probably doesn't surprise you to learn that in normal adults, cognitive ability, things like reaction time, fluid intelligence, and so on, tends to decline as we get older. These researchers wanted to know whether that same pattern holds true in a sample of university professors. Do university professors show age-related declines in cognitive ability? So, very simple study here. They recruited a group of 72 college professors who ranged in age from 30 years old all the way up to 71 years old. And they had them do a reaction time task on a computer to measure their cognitive ability. Basically, they wanted to see if there was a relationship between the professor's age and their reaction time. Now, the one thing to keep in mind about this is that a higher reaction time actually means you're slower, right? So low reaction time indicates higher, better cognitive ability, whereas slower, higher reaction time indicates lesser cognitive ability. Our data file here is called oldprofessors.sav. For each professor, we know two things. We know how old they are. That's our first variable, age. And we know their average reaction time in milliseconds, which is that second variable, RT, on the right. As a reminder, here's how we're going to set up our analysis. We're going to go to Analyze Regression Linear. In this case, our X variable is age, and our Y variable is reaction time. Now, if we wanted to just do everything we did before, right, the t-test and alpha and b and Ramsey and r squared, we could click OK right now, and we would get all of those things, right, as we've already seen. But instead, we're going to click a few extra things that we haven't clicked before. That's going to give us some additional information about outliers and about whether those assumptions that we just talked about are satisfied or violated. So we're going to have to dip into these SPSS menus and click a few more boxes before we run the test. The first menu we're going to dip into is the Save menu. And in this menu, we are going to click three things. The first thing we're going to click is under where it says residuals, we're going to check the box next to unstandardized. So what this is going to do is SPSS for every individual participant is going to calculate the unstandardized residual for that participant. We could do this by hand if we really wanted to, right? We know each person's score, and we could use the regression equation to figure out their predicted score, and then we would just find the difference between what we thought their score would be and what their score actually was. That's what the residual is. Instead, we can ask SPSS to just do it for us, for everyone. So by checking this box, as we'll see in a few minutes, when we run this test, what SPSS is actually going to do is it's going to create a new variable under data view where for each participant, we not only know their age and their reaction time, but we also know their residual. We also know how far off our prediction was of what that person's reaction time was going to be. The other two boxes we're going to check are two different ways to check for outliers when you're running a regression. They're both named after the people who developed them, which we'll talk about in just a minute. One is called Mahalanobis, the other one is called Cook's. So for now, don't worry about it because we're going to come back to that in just a second. Check those two boxes, and what SPSS will do, similar to the residuals, is it will calculate for each person their Mahalanobis distance and their Cook's distance, which we can then use to see if we have anybody who's an outlier. Okay, so we're done in the Save menu. Let's now go into the Plots menu. No matter what our variables are, the Plots menu is always going to look the same. It gives us this same list of options, which makes things a little bit easier for us. What we're going to do in this menu is we are going to create what is called a residual plot, okay, which is exactly what it sounds like. It's taking each person's residual score and putting them on a graph. We'll talk in a little while about what information this actually gives us, but for now, all you need to know is these are the two variables that are going to go in these corresponding boxes. And this is always going to be where these variables go, okay? So anytime you want to make a residual plot, you're going to take the variable called zresid and put it in the Y box. And you're going to take the variable called zpred and put it in the X box, okay? What we'll see in a few minutes is this can actually give us a good hint as to whether our relationship is linear or whether something else is going on here. And it also helps us to check for a couple of those assumptions that we talked about a few slides ago, okay? So just to recap, we do all the same things we did before, right? Analyze regression linear, put the variables where they need to go. In the save menu, there's three things that we have to click: Mahalanobis, Cooks, and unstandardized residuals. And then in the plots menu, we're going to move these variables where they are on the screen right now to get that residual plot as well. So when we run the test, we're going to get the same four tables we got before, but we're also going to get some additional stuff, which we'll see on the next slide. First things first, is there even a relationship between these two things? Sure enough, there is. Okay, so if we jump all the way to that bottom table, we look at the p-value that's attached to that t-test, we see the p-value is 0.003, which tells us that, of course, there's a relationship between age and reaction time in this sample of college professors. Is that relationship positive or negative? Well, all we have to do is look at the t-statistic. T here is positive, so that relationship is positive. As professors get older, their reaction time goes up, which is the same way of saying as they get older, they get slower. About how much slower do they get? Well, we can look at our slope. Our slope here is 3.418. We'll round that to 3.42. So every time x goes up by 1, in other words, every time a professor gets a year older, we expect their reaction time to go up by 3.42 milliseconds. Okay, so every year they get older, we're expecting them to get about 3 milliseconds slower. By the way, this is a good example of a situation where knowing alpha doesn't really help us a whole lot, right? Remember, alpha is the predicted value of y when x equals 0. In this case, alpha is about 431 milliseconds. Why doesn't that make sense? In order to explain that, we'd have to say, well, if there was a professor who was 0 years old, we would expect their reaction time to be 431 milliseconds. That obviously doesn't make sense, right? Because we're not going to have a professor who's 0 years old. So that is still mathematically where the line crosses the y-axis, but for a variable like age, you're not going to have somebody who has an age score of 0. The next thing we want to do is check for outliers. Did we have any really unusual professors in our sample? Maybe a young professor who was unusually slow, maybe an old professor who was unusually fast, and kind of bucked the trend of, getting slower with age. As we saw a few minutes ago, there's two different ways that SPSS can calculate a number to see whether there's outliers or not. And they're, again, named after the people who created them. The first one is called Cook's distance. Now, what it means isn't so important, but you're going to need to know how to interpret the number, right? What does it actually mean? The problem with Cook's distance is people don't really agree on how to interpret it. Most people say that if there's a Cook's distance, if a person has a Cook's distance of more than 1, that they're probably an outlier. But other people follow different rules. So I don't usually use Cook's distance for that reason, because people kind of treat it differently. The other option, I would even venture to say the better option, is called the Mahalanobis distance. Now, each participant, as we'll see on the next slide, is going to have both a Cook's distance and a Mahalanobis distance. For the Cook's distances, we're going to look at them and we're going to ask ourselves, is this number greater than 1 or not? And if it's greater than 1, it suggests that person is probably an outlier. For the Mahalanobis distance, the number that we're going to compare it against is 3.84. Okay, that's always going to, as long as we have one predictor, that's always going to be the number that we compare it against, 3.84. Don't worry about why. Okay, all you need to know is that for each participant, they're going to have a Mahalanobis distance, and if their Mahalanobis distance is greater than 3.84, we're going to consider them an outlier. Since we checked those boxes back in the save menu a few minutes ago, after we run the test, if you jump back into data view where our variables are, you're going to see that there's some new variables there that weren't there before. Each participant, we not only know their age and reaction time, but we now also know their Mahalanobis distance, which SPSS calls Ma1, and we know their Cook's distance, which SPSS calls Ku1. So we could either, kind of skim through the spreadsheet here and look for numbers that are greater than 1. Or better yet, if you remember this from last semester, you can actually right-click on the variable name and you can sort everyone from highest to smallest number. That's an easy way to check to see if we have any outliers here. Now, as it turns out, none of the professors in this sample have a Cook's distance greater than 1. So if we're using Cook's distance, we would say there's no outliers. However, like I said a minute ago, Mahalanobis distance is probably the better way to go. We want to see if anybody has a Mahalanobis distance greater than 3.84. On the screen here, we see there's at least one professor here that has a score greater than 3.84. This professor, who's 71 years old and unusually fast, their Mahalanobis distance is 4.28, right, which is greater than 3.84. So we look at that person and we say, what's going on here? Now, here's the thing about outliers, right? We should look into this because this person's score is definitely weird compared to everyone else, right? This person's 71 years old, but they're also responding super fast. Now, just because they're an outlier doesn't necessarily mean we should throw them out, right? We have to have a good reason to throw someone out. It's very possible that this person really is just old and fast. That doesn't mean they shouldn't be included in our sample. However, it's also possible that for whatever reason, this is a mistake, right? Maybe this was a typo, for example. Maybe they're actually 41, and I meant to put in their age as 41, but I accidentally hit 71. Maybe the computer malfunctioned, right? When I was recording their reaction time, maybe there was some kind of weird malfunction and it made it look like they were responding a lot faster than they actually were. So when you see an outlier like this, you should definitely check it out, right? And see if there is a legitimate reason why you may need to change or remove this person's data. But if they really are just a genuinely unusual person, you keep them in, right? You wouldn't get rid of them just because they're different. So here's how I always deal with outliers. I always run the analysis twice. So we can run the analysis once with everybody, including the outliers, and then we run the analysis again with everybody except the outliers, and see if the results change, right? If the results don't change, then the outliers didn't really change the outcome of our study or not, really, right? So that's usually my procedure here, is run the test with outliers and without, compare the results between those two tests. If they point to the same conclusion, you say, great, regardless of whether the outliers are included or not, I still get the same results. So if you wanted to do that, here's how you would do it. SPSS has a function called select cases, where you can selectively filter out people who don't meet whatever criteria you want them to meet. So in this case, anybody who's an outlier is a person whose Mahalanobis distance is greater than 3.84. So we can ask SPSS to filter those people out so that we can run this regression again and see if our results change when we exclude those people. So here are the steps you'll need to follow if you want to exclude outliers before running a regression. First, you're going to go into the data menu and you're going to go to the option called select cases. When you click select cases, that window that you see in the middle is going to pop up and you're going to click the box that says if. Now, this is where we tell SPSS what condition has to be met in order for a person to be kept. Okay, who do we want to keep in our sample? That's what we type in this box. We want to keep anybody whose Mahalanobis distance is less than 3.84. So that's what we're going to type in this box. We're going to type Ma1, which is the name of the Mahalanobis distance variable. We're going to put a less than sign, and then we're going to type 3.84. This is our way of telling SPSS we want to run this analysis again, but we only want to include people whose Mahalanobis distance is less than 3.84. After we type that in, we click continue. That's going to take us back to that middle window. And what we should now see is next to that if button, whatever we just typed, the Ma1 less than 3.84, is now going to appear next to that button. And then we'll be able to click OK to filter out the people that we don't want. Once you've done that, to check to make sure that it worked, At the bottom right-hand side of the screen, you should now see a little message that says filter on. Okay, so what that's telling you is that some people in your sample are being not included right now, right? And in fact, if you remember correctly, the outlier was person number 52. Person number 52 is gone, right? If you read the numbers in each row down the left-hand side here, it jumps right from 51 to 53, which is telling us that any analysis that we run right now is going to be run without that person. As long as the filter is on, any analysis that we do, whether it's a regression, t-test, scatter plot, whatever, is going to be done without that person that we just excluded. So we already ran the regression with all 74 professors. Now that we've excluded the outlier professor, let's run this same analysis again and see if excluding them changed our results at all. Here are the same results that we saw earlier. So p-value of 0.003, t-statistic of positive 3.11. These are the results of the regression when we included everybody. Now that we've excluded this outlier person, here's what our results look like. Our p-value actually went down a little. Our t-statistic went up a little. Our slope went up a little. But the overall pattern of the results is the same. Okay? When we included the outlier professor, there was a significant positive relationship between age and reaction time. Even after we excluded them, there was still a significant positive relationship between age and reaction time. So this is a good example of how this outlier, even though they were unusual, and yeah, okay, the alpha and B changed a little bit when we took them out, the overall pattern of the results didn't change. So regardless of whether we include them or not, the conclusion is the same, which is that age was in fact a predictor of reaction time. Important thing, whenever you filter people out to run an analysis like we just did, before you run any other analyses, make sure you go back into that menu, data select cases, and undo what you did before, right? So you're going to unselect if, and you're instead going to go back to the default option, which is select all cases. You want to make sure that when you take people out and you run an analysis with those people taken out, you then put those people back in. Otherwise, you might forget, go run another analysis, and without realizing it, you've excluded people when you didn't mean to. Okay, so we've seen how to check for outliers. And assuming we find any outliers, we've seen how to filter them out and how to run the same analysis without the outliers to see whether they changed our results at all, which in this case, thankfully, they did not. The other things we should check for are these three assumptions that I mentioned earlier. We need to check to see if the residuals are normal, linear, and homoscedastic. Normal means exactly what you think it means, right? Normal means that most of the dots are fairly close to the line, and there are few dots that are relatively far away from the line. So basically, if we were to take all of these residuals and plot them on a graph, it should look kind of like a normal distribution, right? Where most people have fairly small residuals that are close to zero, and fewer people have really big residuals that are farther away from zero. So if you jump back to data view, since we clicked that box in the save menu earlier, we now can also see for each participant what their residual score was. So remember, this is telling us how far off our predictions were. So for participant number 16, for example, they're 68 years old. Their reaction time is about 661 milliseconds. Our prediction was almost right on the money, right? Our prediction was only off by 2 milliseconds for that person. So they have a very small residual. But for person number 20, for example, this is a person who is 32 years old and their reaction time was about 364 milliseconds. Our prediction was pretty far off, right? We were off by 176 milliseconds, so we have a pretty big residual for them. This variable is called res1, and we can treat it just like we treat any other variable. So back in the fall in Design 1, you probably talked about how to check to see whether a variable is normally distributed or not. You probably haven't thought about that in a while though, so here's a refresher. of how to check to see whether a variable, in this case the variable res1, is normally distributed or whether it is skewed. There's two different ways we can do it, and thankfully both of those ways require the same steps. So the first thing we're going to do is we're going to run the explore procedure. We're going to go to Analyze, Descriptives, Explore. We're going to pick the variable that we're interested in. In this case, it's res1, the unstandardized residual for each college professor who participated in this study. And we're going to put that variable in the box called dependent list. But before we click OK, we're going to go into the plots menu and check the box that says normality plots with tests. This is going to give us a couple different ways that we can check to see whether this variable, whether these residuals are normally distributed or not. One of them is I call a skewness test. So in that very first table in your output, it gives you a whole bunch of descriptive statistics about these people. It gives you the mean, standard deviation, the range, the IQR, all the stuff that you probably talked about way back in September. It also gives you a statistic called skewness, and it gives you the standard error of that statistic. So two numbers right next to each other in the row titled skewness. All you're going to do here is you're going to take the number on the left, which in this case is negative 0.069, and you're going to divide it by the number on the right, which in this case is 0.283. Okay, so if you divide that out, you'll have to use your calculator for this one. Negative 0.069 divided by 0.283 comes out to negative 0.24. Okay, so that is the result of our skewness test. Now, as you probably learned back in the spring or back in the fall, what we're looking for here is a number that is anywhere between -3 and +3. Okay, so if once we do the skewness test, if the number that we end up with is within 3 points of 0 in either direction, we tend to say we're good, right? It's normal enough. It's not so skewed that we have to be worried about it. Negative 0.24 is very close to 0, right? Well within our boundaries of plus or minus 3. So we would look at this and we would say, yep, we're good. These residuals are not skewed. The other option we could use is a more formal test of skewness. We call it the KS test. Again, it's named after the folks who developed it. This one is a little bit more confusing. I personally prefer the skewness test, but if you want to use the KS test, what you would do is look at the p-value for the KS test, which in this case is exactly 0.20, 0.2000. And here's the weird thing about this test. We're used to thinking of low p-values as being a good thing. In this case, a big p-value is actually a good thing. Okay, so for the KS test, a p-value of greater than 0.05 means that we are not skewed. It means that we have normally distributed residuals. If this p-value were less than 0.05, then we might have a problem. So in this example, no matter which way we do it, whether we use the skewness test or the KS test, it points us to the same conclusion, which is that these residuals are in fact normally distributed, so we don't have anything to be worried about. So that's one of our assumptions done. We checked for normality, and the residuals are in fact normal. We also asked for a residual plot. This is where we did the Z-resid and Z-pred in that plots menu. This is the graph that it gives us. Now, believe it or not, this relatively simple looking graph is going to allow us to test those other two assumptions, linearity and homoskedasticity. And the way we're going to test those things is just by looking at the overall shape of the dots on this graph. Okay? So when you see a residual plot like this one, the first thing I want you to do is I want you to envision that there's a horizontal line at 0 on the y-axis. Okay, so that red line is just right at 0. The next thing that I want you to do is imagine that you were to draw a shape that goes around all of the dots. Okay, a shape that sort of captures all of the dots on the graph. If both of these assumptions are met, that shape should be rectangular, right? Because what we're looking for here is the dots, no matter where we are on the graph, right? No matter at what point on the x-axis we're at, the dots should be pretty well evenly dispersed both above and below the line, so that if we were to imagine drawing a shape around them, it would look pretty damn close to a rectangle with our horizontal line going kind of through the middle of the rectangle. So in a case like this, we envision this green rectangle. We say, okay, that's kind of what we were hoping for. This looks like both of those assumptions are met. Now, the obvious question is, what if those assumptions are not met? What will this graph look like? Here are some examples. The graph on the left, if we were to draw a shape around the dots, it would be a semicircle. Okay, it would be like a U shape, a crescent, a semicircle, however you want to think about it, because there's a clear curved pattern to the dots. When that happens, the graph is telling us that the assumption of linearity is probably violated. Okay? Again, it's not the most scientific way to do it, but if we were to draw a shape around these dots, it would look like a semicircle. Now, as we'll see in a little while, when this happens, it suggests that the relationship is actually U-shaped rather than linear. For the graph on the right, if we were to draw a shape around those dots, it would look like a triangle or like a wedge, right? With the line going right down the middle. When the residual plot takes that shape, it suggests that homoskedasticity is violated. That's just a fancy way of saying basically on one side of the graph, all of the dots are really close to the line, and on the other side of the graph, the dots are much farther away from the line. So we have a scatter plot that's kind of lopsided rather than nice and pretty and linear like the ones that we saw last week. Okay? The reason that's important is because it's telling us that our ability to predict the thing that we're trying to predict is actually different depending on a person's X score, right? So it creates a problem for us because our predictions are sometimes really good and sometimes really bad, but it's not in a random fashion. There's sort of a problematic pattern to it, okay? So to quickly summarize, I cannot make it any more straightforward than this. You look at your residual plot. You imagine drawing a shape around the dots. If it's a rectangle, that's good, right? That means that both linearity and homoskedasticity are probably met. If it's a semicircle, not good. It means that your assumption of linearity is probably violated. And if it's a triangle, also not good. It means that your assumption of homoskedasticity is probably violated. Here is your optional practice problem for next week. Since we're not able to meet today, I especially encourage you to give this one a shot to make sure that you understand everything that we talked about in this video. So I have a data file online called boozetemp.sav. You'll see a screenshot of it on the next slide. But basically, this is based on a study that we talked about last week in passing. A researcher wanted to know if climate is a predictor of alcohol consumption. So they collected data for 186 countries. And for each country, we know two things. We know the average annual temperature in that country measured in degrees, and we know the average per capita alcohol consumption in that country. So we want to know if there's a relationship between how hot a country is and how much alcohol people tend to drink in that country. So for practice, here's what I'd like you to try. First, just run the regression, okay, with average temperature as your predictor, your X variable, and alcohol consumption as your outcome, your Y variable. Tell me whether those two things are related. Is the relationship positive or negative? Tell me what alpha means. Tell me what the slope means. Okay, so basically do all the stuff that we did last week. You could also take a shot at interpreting R squared as well. How much of the puzzle have we figured out, right? How much of the variation in alcohol consumption is explained by temperature? Then I want you to try some of the stuff that we did today. So in the save menu, you're going to check those three boxes: unstandardized residuals, Cook's distance, and Mahalanobis distance. The first thing I want you to do, as we just saw, is run a skewness test on the residuals and see if the result is between plus or minus 3, right? Which would tell us that there is not a problematic amount of skewness. In the plots menu, I also want you to generate a residual plot like we just did. And based on the shape of that plot, I want you to tell me whether it looks like linearity and homoscedasticity are met, or whether one of them is violated, and if so, which one you think is violated based on the shape. And then lastly, I want you to use the Mahalanobis distance to see if there are any outliers. If there are, I want you to tell me how many outliers there are, and I want you to run the analysis again with those outliers filtered out. So you'll have to go to select cases, filter out any country that has a Mahalanobis distance that's too high, run the analysis again, compare the results side by side, and see, what's your new p-value, what's your new t-statistic, and most importantly, is the overall pattern of results the same as it was before. Okay, so here I actually have, I'll skip through it right now, but I actually have all of the results on the slides, so you could immediately check your work if you want to, and obviously bring any questions that you have to class next week. As always, I encourage you to do these things in pairs, right? Either do it together, or you can each do it individually and then compare your answers, talk through any differences that come up. But I do think that talking through this stuff really is helpful. Okay, this is the last example that we're going to do today, and it is not something that I am going to expect you to know how to do. It is not something that I am going to test you on. So, strictly speaking, if you want to stop the video right now, you can. Or if you want to stick with me for another maybe 5-6 minutes, I want to show you something that, again, I'm not going to test you on, but something that SPSS is capable of doing that might end up being useful for your own research outside of this class. Here's the study that this example is based on. It was a study of risk aversion. So they put people in a situation where they had the opportunity to make risky decisions. Specifically, they had to answer a bunch of questions like this one. Imagine you had to choose between these two options, okay? Option A, you have a 50-50 shot of getting $13. So you either get $13 or you get $0. Option B, you definitely get $5, okay? So option B is obviously the safe option. You're guaranteed $5. Option A is the risky option. You might get $13, you might get nothing at all. The goal of this study was to see whether a person's testosterone level predicts how frequently they choose the risky option as opposed to the safe option, okay? So for the purposes of this study, our X variable is a person's testosterone level. They, probably just spit in a cup and measured their testosterone level. Higher numbers mean a higher testosterone level. Y, our outcome variable, is the number of risky decisions that person made. Okay, so the goal here is to see maybe people with higher testosterone make more risky decisions. Maybe people with higher testosterone make fewer risky decisions. We'll find out. Here's the data file, riskaversion.scv. Again, for each person, we know two things. We know their testosterone level, which is on the left, and we know what percentage of the time they took the risky option as opposed to the safe option. So we run the linear regression, analyze regression linear, testosterone's our predictor, risky behavior is our outcome, and womp womp, there's our results. P-value of 0.300. No relationship between testosterone level and risky decision making. It's normal to feel disappointed when this happens, right? I mean, maybe for your first year project, your thesis, your independent research, you go through all this trouble of designing this really fancy study and collecting, testosterone data and all this participants and time and money. And then at the end of the day, it's like, well, I expected there to be a relationship, but there wasn't a damn thing. But instead of being disappointed, maybe there's something else going on here, because we just jumped right in to run the test. We didn't check any of those assumptions that we talked about a little while ago. We didn't check for outliers. We didn't check for linearity or normality or any of that stuff. What if we did that? So what I did here is I ran the analysis again, but now doing, in addition, not only the stuff that we learned last week, but also all of the new stuff that we talked about this week. Here's for each person their residual score, their Mahalanobis distance, their Cook's distance. And, like we just talked about, we could go through and look. It looks like there's at least one person who's an outlier. We could filter them out, see if that changes our results. There's no Cook's distances greater than one. The residuals are normally distributed, right? So if we ran a skewness test on the res1 variable, we'd do negative 0.131 divided by positive 0.181. That's going to be well within plus or minus 3, right? It's going to be less than 1. So, some of the assumptions are met. Maybe the outliers matter. I don't know. But what about that residual plot? Here again is a refresher on how to get it, right, and where the variables go. If we ran a residual plot on these data, the residual plot would look like this. Now, based on what we know about residual plots, we kind of envision drawing a shape around all the dots. Rectangle, good. Semicircle, bad. Triangle, bad. Bad may not be the right word, though, right? Because if we look at this plot, if we were to draw a shape around this, it would be a semicircle. We don't have a lot of dots in the lower left-hand side of the graph. We don't have a lot of dots in the lower right-hand side of the graph. So we have sort of like a wedge shape if we were to connect all these dots to each other. As we saw a little while ago, when we get this wedge shape, it suggests that the relationship is not linear. But that doesn't necessarily mean that there isn't a relationship at all. Maybe there's actually a U-shaped or curvilinear relationship. Now, again, this isn't something I would ever expect you to do or something I would test you on, but just for your own curiosity, SPSS can actually run a whole bunch of different types of regressions. We've only talked about, and we're only going to talk about linear regressions, right? Assuming that the two variables are related to each other in a linear fashion, but that doesn't necessarily have to be the case, okay? So if we want to test for a nonlinear relationship between two variables, here's where we can do that in SPSS. Analyze regression, and then right under where we usually go, which is linear, there's another option called curve estimation. Now, when you click on curve estimation, it looks kind of similar to the linear menu, right? We're still going to put testosterone as our predictor. We're going to put risky decisions as our outcome. But now there's a whole bunch of different types of shapes of relationships that we can look for, right? We can test for a linear relationship, but we can also test for a quadratic relationship, which is a U shape. We can test for a cubic relationship, which is like an S shape. We can test for a logarithmic relationship, which kind of looks like this, like it kind of starts steep and then flattens out, right? Just because a relationship isn't linear doesn't mean there isn't one. And there may be situations in which you might expect to find a nonlinear relationship, and here's where you can check for that. So what I've done here is this. I clicked two boxes. I checked linear. We already know how that's going to turn out because we already ran it, but I wanted to see it again. And I also checked quadratic to see whether there might be a U-shaped relationship between those two things. So when I run this regression, it's going to tell me which of those things is a better explanation for the shape of the relationship between these two variables. So here you get a table with two rows. The top row shows us whether there's a linear relationship or not, which we already know there wasn't, right? Because we already ran that. The second row tells us whether there's a quadratic relationship or not. As it turns out, there was. So for the linear relationship, p-value of 0.3, not significant. But for the quadratic relationship, a p-value of 0.002. So if we had just given up, right, after we found that there was no linear relationship, if we had just kind of thrown up our hands and said, well, I guess I just wasted all my time doing that thesis project, we would have missed this really cool curvilinear relationship that we only discovered because we checked that assumption. So there is an advantage to looking for this stuff because kind of like we saw with the T-Rex last week, when you go digging, sometimes you find stuff that you didn't expect to find that's really interesting. That is, in fact, how this study actually turned out. As it turns out, when they looked for a relationship between testosterone level and risk taking, they didn't find a linear relationship, but they did find a U-shaped relationship. As it turns out, people who have really low testosterone levels and people who have really high testosterone levels, they all tend to make riskier decisions. Whereas people whose testosterone levels are kind of average tend to be the most risk averse. So as you can see in the scatter plot on the right, it's not linear, but it is U-shaped. And we wouldn't have known any of that if we hadn't checked our residual plot and seen that semicircle on there. That's all I have for today. Thank you for your time and attention. I'm sorry we didn't get to catch up in person, but I will see you back there next Tuesday. If you have any questions about anything at all, as always, shoot me an email. Otherwise, we will begin class next week by really quickly reviewing everything in this video, including especially that booze temp practice problem. So please do try to make that a priority so that we can start talking about logistic regression next week. See you then.